So, good evening and welcome to the week 11 of the live interactive session of Fundamentals of Micro and Nanofabrication. The course instructors are Professor Sushovan Avasti and Professor Sankar Selvaraja from IIC Bangalore. I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. So, till now, this is a brief about me, the class link, YouTube link, and my contact details. And in addition to this, there will be an additional session on 10th, that is day after tomorrow at 6 p.m. where you can join. That will be an overview of the micro and nano fabrication from starting to end in one lecture. Micro and nano fabrication at 6 p.m. Okay. So till now we have learned about different micro and nano fabrication processes. Now how to combine this together, because they cannot be like we are doing all these processes to achieve one thing, like one device. So there must be some correlation, there must be some understanding that how these processes will be linked together to get our desired output and increase our performance as well as increase the yield, like quality and yield. Okay, so one thing that comes in this is chemical mechanical polishing. Okay, and this is used to flatten wafers after they are processed. That means in the first lecture, after learning about clean room and all, we learned about wafers. We talked about how these wafers are polished and what is their manufacturing process and all. But once these devices are made, and we have seen that uh, in many processes we are depositing, we are removing, a lot of things are going on. So there must be some uneven surfaces as well as the structures that we have made and that may need to be in a plane that will not that might not be in plane due to some errors, as we have seen, as well as there are some conformal issues, like on a wafer, if we are depositing a metal, say, throughout, the thickness will have some variation. Although we might have tried to minimize it, we might have tried to have the minimal variation, but there will be some variation. So those variations have to be cleared, and a uniform surface is to be given for the next process, subsequent process, because error in one layer will lead to an error in the more error in the second layer, third, and that will lead to more in third, and so on. So we have to deal with this, and this is generally done using a process called as chemical mechanical polishing. That means this is a combination of a chemical as well as a mechanic. It is a mechanical process where the polishing, just like you might have seen workers polishing steel surfaces to get the shine, as well as other mechanical works where after the surfaces are clean, they are polished. A similar process has to be done. So why we need planar surfaces? Because as I said, we are mostly dealing with lithography, and lithography will have issues with depth of focus. When we have variation of metal, if it is a metal layer, if we have variation of thickness, that will lead to resistance variation, that will lead to delay and timing error. So we want the resistance to be uniform. It must not be like lumps of high and low resistances and like that. It should be uniform. And if we have some thin metal line and some thick metal lines, so Functional failures can occur from thin metal lines or misaligned contacts, and this can happen when we have non-planar surface. So planarization ensures uniform layers and reduces the failure risk. So what are the key elements of a chemical mechanical policing? One is policing head. Okay, like you see here, uh, you are able to see this figure. So second is policing pad. So policing pad or the absorbent pad that is sorry, that is attached to the policing head. So this is simply a mechanical thing, you can say, which is having a it will be motorized along with putting a pressure, and that will be containing a policing pad or adsorbent layer. And what this adsorbent layer will adsorb, that is a slurry that contains the abrasive particles for material removal. So these are the things that will actually do the uh, polishing. The actual polishing will happen due to the slurry that will contain some abrasive particles. And then we have conditioner that keeps the pad rough for continued polishing. Okay. So to simply understand what is this CMP, say we have a dielectric that was deposited like this. So we ideally we might have thought to deposit, say we wanted a deposition like this, or maybe a deposition like this. But due to our process errors, there is some uh, non-uniformity there. Okay. So what if we directly go for our lithography? Then we might not get a perfect pattern like this. So if we are going for CMP for the dielectric layer, we will get a planar layer. And then we do lithography, we'll get better results compared to what was expected, what was better results to what was about to happen when we would have directly done the lithography process. Then after that, we did the metal deposition, say, and if we just wanted the metal to be filled in this area that was opened by the dielectric layer, so we can directly do the CMP. That is, we flatten it and all the metals will be removed except for these areas that we wanted. So this is also a technique that is sometimes used for these forming the content, and as well as one advantage main thing is that if we see this part, the planar structure planarized leads to better yield. Okay. So that is one big reason, as well as it will help us in better yield or throughput for the subsequent process. Okay. So what are the stages of a CMP? First is smoothing. This reduces sharp topography features. So there can be some features, say on the wafer, Uh, Suppose we deposited something and it is non-conformal, it's fine. But there is suppose a spike like this and here like this. So first is smoothing that will reduce this sharp edges, sharp topography features. So then second what we will do is local planarization. That means uh, planarize in this area, like small area is planarized first to get a almost flattened surface. Then a global planarization will be used. So the next is the whole surface will be planarized in one go. That will uh, achieve overall flatness. So first, very small sharp features are removed. Then small variations are flattened out. Then third is globally the whole wafer will be uh, flattened or planarized. So how these materials are actually removed? The material removal rate depends on the pressure and relative velocity between wafer and pad. So it is like it can either be of both the types, that either the wafer and the pad we saw, pad with the adsorbent material. Okay, these two are moving with respect to each other. They both of them might be moving, or one of them might be moving. Say wafer is fixed, and we are moving this pad. But in some cases, to make it faster, and it can either be that the wafer and the pad both are moving. Okay, as well as we are applying some pressure on top of this pad. So it is pressed with some hardness to the surface of the wafer. So it will depend on two things: how much material is removed or how much material we intend to remove. That will depend on the pressure that is given and the relative velocity between wafer and pad. Either both of them will be moving or one will be moving with, but with respect to one another they are moving, and this relative velocity will determine the material removal rate. So there is Preston's law, that says that removal rate, say R, is proportional to the pressure applied and the velocity V of the movement. So is it that we want the pressure to be same? It depends on the type of uh, feature that we have or type of the imperfections we have. So more pressure is applied on raised features and less pressure will be applied for uh, almost of the correct size. Like if we have a feature like this, some non-planar deposition has occurred, and if we want to planarize this, so in what area the planarization will be more? If we are saying A, B, C, D, and say E. So can anyone tell me in which area the most in which area we will give the uh, highest pressure for planarization in all of this?
A.
A and D. Like if you see A and D, they are at a higher position. And in which case we will give the lowest?
Like remaining E, B, and C.
Yeah,
E will be lowest.
yeah. E will be lowest, or I think something between A and B, because that is the lowest point here. If we if we draw a straight line, we see that the area between A and B, there is the lowest point. So ideally we will get at a point somewhere at this level, right? I think that is actually the whole figure itself is slanted a bit. So yes, so the points where we have features which are out like protruding or coming above the feature, there we will need more pressure. So pressure distribution has to be decided to get the optimal material removal. So how do we achieve this is fine when we are having different materials. Okay. So once this local planarization has been done, then we go for global planarization. So how do we achieve it? First, we have already seen that the goal of CMP is to achieve zero planarization angle, that is perfect flatness. Okay. So for the global planarization, that means all the areas should have same planarization. We have to understand the first is pad and the slurry conditions should be properly controlled and optimized. Pressure and time. Even if you are putting something with less pressure, but doing it for a longer time, that will lead to more material removal. Okay. And we have to understand when to stop the process for avoiding the material loss. It should not happen that we keep on going to planarize. Sometimes it might happen that the level of planarization is not very perfect, but if we go further, we will actually lose whatever we have already made. So such things has also to be kept in mind when we are going for planarization for subsequent processes. So what is the configuration? Just like we saw in the image, pad, wafer holder, slurry, and conditioner. So the wafer will be kept on, so that if we have a single wafer system, say, that will be hold on a holder. There can be a different type of holders, like some some of them have like mechanical holder which are screwed, like using some slots and all. Some can have vacuum based systems that you keep the pad, switch on the vacuum, and it will be hold tight. It depends on the manufacturer as well as the design. Okay. Then pad, that is the on if we are seeing the pad what is there, and then below it the adsorbent material. So this whole thing is we are calling as pad. Then the slurry, what kind of slurry or the uh, chemical we are using, and the conditioner that will keep this whole process running. That means in a sense a lubricant, if we are talking in terms of a common language, that it will keep this whole process going on. If it dries this slurry, it will not facilitate the CMP. So what are the configuration in which they can work? One is rotary configuration, in which both the pad and the wafer rotate. Pad is rotating as well as the wafer is rotating at the bottom. Second is orbital. Wafer rotates while the pad follows an orbital path. So rotary is when both of them are being controlled randomly, like they don't have a sequence. In orbital, the wafer is rotating and the pad is following a orbital path. Like it is just a just like it is moving on its axis at a point, and the wafer is moving like from here to next, like that. Second is linear, that is wafer and pad move in linearly opposite direction. That means wafer is moving like this and pad will move like this. But in all these cases, the pad will keep rotating. It is not stagnant, like it is not rubbing like a duster. It is like it is also rotating, even if it is going linear, but it is rotating around its axis. It has an orbital. path always. Okay, so it can be moving in this direction and the pad will move in the opposite direction. That is a linear. So like that, one line rastering, you can say one line planarized, then the whole wafer will be moved, and then again next line like that. Then is fixed plate. The wafer moves, but the pad remains stationary. So in this case, the pad will be fixed, no orbital motion also. The wafer itself will give the orbital motion as well as the linear motion. All the motions is due to the wafer or the wafer holder only. Based on this, you can understand that the uniformity will also be affected by the configuration in which we are running. And according to our need, we, we might need to vary the configuration. Sometimes it is possible in the same machine that we have rotary and orbital motions possible, or rotary and linear, all the four motions can be possible according to the manufacturer, and we will have to decide what will give the best result for us. So uniformity is controlled by pressure distribution across the wafer. Adjusting pressure locally using so the control of this wafer head, the wafer assembly that is moving, has to be done locally. More local, that means more control for a specific area, better will be our output. So it has to be done using some advanced wafer head technology. That means more computation based, you can say more the computation involved, better will be our output. So as well as we have to take in care that we have to apply differential force, because at the center we have to put higher force, and at the at the edges of the wafer we have to you say when we are doing the CMP, we have to apply lower force. Why? Because if the wafer is rotating from the center, that means its angular velocity at the sides will be more compared to the angular velocity at the center. That is why we have to apply different amount of forces. So we have to balance the pressure and the velocity for uniform material removal for different areas. We have to understand and evaluate and then determine the then we have to feed what will be the different value of pressures for different area. So the relative speed is one thing that is controlled by different type of configuration of this configuration of the movement between this pad and the wafer. Second is the force, the differential force that we are giving for different areas of the wafer when we are doing it locally. And once we have achieved that locally, then we will go for the global one. And in case of global also, if we have a single pad, we cannot have a uniform force. So the force will also vary. In the center, it will be high. On the sides, it will be lower, because we have different speeds, different velocity that will lead to different value of erosion or different value of material removal. So what are the types of pads and the conditioner used? So pads can be, one is a polymer based, that is soft, uh, soft polymer that is fine for transporting the abrasives. So that the abrasive materials, the slurry, okay, that can easily be transferred using this polymer based. Second type is porous or leather-based materials can be used. Third is polymer sheets, but textured. Text, say it has some dotted or like if we are seeing like removing it and seeing it from the top, like front, it can have some dots or maybe some structures like this to facilitate the movement of slide. It cannot be smooth. This pad is not to be smooth. Okay. After using for some time, these pads will lose the abrasiveness due to deposited slurry and they will need conditioning. They will need cleaning. Okay. So what are the conditioner? They are diamond tip tools that are used to roughen the pad. So this pad will be taken to the condition that will uh, remove the what you say, the deposited slurry in between that will be removed. Okay, and after that it can be reused till it is still like still it is in the process of use, like it is still in the condition to use. Okay, then this polishing will decrease over time. Like same pad, if it is a new one, it will polish very well. Although we are using conditioner, we are keeping everything like we are maintaining it regularly. But over a period of time, these pads will smoothen and they will like they will not polish properly. So we will again use conditioner like that. But after a period of time, these pads will go bad and we will have to replace them also. And what is the composition of this slurry? One main part is the abrasive particle. It can be silica or alumina. The particle size will depend on the smoothness required. That can range from 10 to 300 nanometer. Okay, and the concentration, it is a solution, liquid kind of thing. Okay. So it has you can think of it as a liquid with some particle like powder kind of material mixed made a slurry in it. Okay, so this particle size will determine the smoothness required. Second is the concentration of particles. If we have less concentration, that will uh, take more time to smoothen out. If we have more concentration, it will take less time to smoothen out. Okay. In this case, since it is a solution, the zeta potential and pH are critical for ensuring good particle distribution. So we have to ensure that the zeta potential is ideally zero and pH is neutral, and so that there is no aggregation like this silica and alumina, whatever is the best pH for maintaining the solution characteristic of it, that has to be maintained. That is very critical. So whatever solution we are taking in which this is mixed, that will determine that how much aggregation is there or not. So we have to choose the solution accordingly. So this slurry enables the smooth material removal without damaging the wafer surface. So if we would have directly done it physically, say we made if we are going with silica or alumina only, if we made a pad of silica and we are polishing it with polishing the wafer with silica or alumina, that in that case it might damage our wafer also. But here, although it is being done physically, but the actual removal is happening due to these abrasive particles, not a pad. So now there can be some issues when we are talking about CMP. Okay, one is dissing, that is when polishing is not stopped on time. This leads to excessive material removal. So this is more relevant when we are talking about softer materials, and that will create a concave structure. Okay, like this structure. So a lot of local dissing mostly happens in case of local polishing, local area. In a local area, a concave structure has formed. Second is erosion, occurs due to density variation of the in the wafer. That is in different areas or different materials. Uh, like if we have different materials in different areas of the wafer, like tungsten and silicon oxide. So although the same process is being applied over it, say this is Ti, this is SiO2, okay, but they might not lead to global uniformity because the removal rate is different for the same process, and that can lead to some erosion. That means in some non-uniform, like in some area you see SiO2 is at a higher position than the Ti because there is some difference in the like globally it is not yet blended. That can be an erosion. So after CMP is done, cleaning is essential because we have put abrasive a slurry of abrasive particles that might stick and that will remain on the surface of our wafer. So there we can use brush cleaning or ultrasonic cleaning. So it is simply like a brush is used to clean all the materials or sonicate it in proper solution so that whatever abrasive material is left that will dissolve into the solution and we will get a clean wafer, because any particle left will lead to contamination in our subsequent processes. And so we can say that CMP is a dirty process. That means it will actually contaminate our whole wafer. So cleaning is very important for our subsequent steps. So in short, CMP is crucial for achieving planar surfaces in semiconductor fabrication. Proper configuration, pad conditioning, and slurry selection are key to CMP. And flatness and smoothness are achieved through care, carefully controlling the process control and post cleaning. Because this is a very important part because we went for CMP so that we can uh, achieve better throughput. But what if this process itself contaminates our wafer? So clean post CMP cleaning is a crucial part in this whole process. Any questions still here? Yes, anyone?
No, no, no questions for now.
Okay. So next is, since this is the one part that is like we say between uh, one like between one process to another process, what is to be done. But when we are talking about process integration, there are other uh, things to be taken care of, and one is the design for manufacturing. That is, when we are designing uh, products, like when we are conceptualizing the product or in this case the circuit or the way the final structure of device. It so happens that many a times, like theoretically, or we may think that this will happen, but the manufacturing limitation is there, and that is not kept in mind. Like suppose that someone can say that I will do this, that I will make in the gate area, I will put a dielectric and I will create a, say this will be of 50 nanometer, and I will create a metallic structure, like metal electrodes over it, or say another dielectric, say HFO2 over it, and this overhang will be say 200 nanometer. So if we put it in, even if we put it in a simulation software, it will work fine and it will give the potential and everything. But it is not possible. It may not be feasible to have such a large overhang supported just by a smaller pillar. So if we have a support of this size and we have a overhang much larger than this, and the thickness is also very less, like its thickness is say 10 nanometer only, so it sustain might not or it will not sustain actually if we are thinking practically. So such considerations are not taken in mind. So when we are taking such considerations in mind, the thing is called as design for manufacturability. That means from the starting itself, when we are designing or conceptualizing, we are keeping in mind that we have to actuate it, we have to uh, manufacture it. It is not that we just have to put it as a concept and like actual manufacturing that someone else will see. It is not like that. So this is quite important and crucial. If the design itself is designed for manufacturability, we will increase the throughput. We will have less number of trial and errors. The optimization time will be less. Losses will be less. Okay. So the objective here is to create design that can be easily and cost effectively manufactured without minimizing, not without, while minimizing waste and errors. So wastage will be less, errors will be less. So that means we will have less trial and errors, less optimization needed, since the design from the starting itself was such that it was thought that yes, these are the limitations that can come, and that those has been like kept in mind. Although it will not be perfect, but it will be somewhat realistic. Why is it important? Because designing with manufacturability helps reduce resource waste, avoid design manufacturing conflict. So, like I said, someone might give such a design, but we we may not get the like when this design goes to a person who actually fabricates or manufacture, he will say no, this is not possible, or he might try and waste a lot of resources and then declare that no, this is not feasible. Okay. And or it might happen that he it is made like this, but in the subsequent process it just breaks, goes out, and whatever things we wanted we will not get. So we want that our products meet performance criteria when fabricated. So we have to understand and account for variability and limitation of manufacturing process in the design phase itself. We don't have to wait for the final, like it some common thing that not even in microfabrication, in any kind of industry, it might happen that someone is waiting for the like they have conceptualized something, the product is made, and at the last, when it is made fully conceptualized, fully like in a physical form, it is made, and then it is tested for the problems, and then again that problem is sent back to the person who designed and all, and then it is this whole process is followed. What if these problems are well, like what are the physical problems, what are the possible problems that can occur is well known to the first designer, the first person who conceptualized, then that will lead to accounting these variabilities and limitations in the design phase itself, and that will lead to like better yield or throughput in minimal time, less time. So what are the types of variability? What are the types of variability? So there can be two type of variability: systemic and random. Systemic variabilities are identifiable and can be compensated. Like suppose that I know in my mask alignment system, like it generally happens in case of the alignment system I am working with. There will there is always a when we like I use a proximity system. So when we bring this mask and wafer closer, there is always a displacement in the direction of x and y, a small amount, and every time it is happening. I know that suppose that uh, this is my alignment mark on the mask and wafer. And what will happen that once it comes close, it always moves a bit rightward, and I know that this much almost 2 micrometer this side and 1.7 micrometer this side. Okay, and this is happening every time. So now I know that I have to compensate for this. Like either I will design my alignment marks such that they are shifted a bit in the opposite direction, or while doing the alignment I will shift in the reverse. Like I will first align properly, and then everything is aligned, then I will shift the whole mask by I know in the x direction minus 2 micrometer and y direction minus 1.7 micrometer, and I will get the result. So these are some systemic variability. That means in a sense a systematic thing uh, where the variation is fixed or defined, or where we can identify it. Second is random variability, unpredictable. It can happen this time, next time it might not happen. Again, it can happen, but it might be happening in some other value, like not a predictable thing. So this kind of random variability are hard to eliminate, like random particle contamination or microscopic fluctuation. Like when we are using the microscope, the alignment we are like the focusing we are doing. Some in some case, uh, like we might be able to focus properly. In the next case, some slight variation can be there. So that is random. That is not well defined. That such an error will occur. So we have to compensate for it. So these kind of variabilities, like systematic or random, affects the design and manufacturability in intra-die, inter-die, wafer to wafer, and batch to batch process. So are you aware with this term die? Anyone?
Yes, the platform, uh, one uh, one chip after we do the dicing on the wafer is a
Yes,
die.
it's a die. Yes, very correct. So wafer is the, in a sense, we can say wafer is the manufacturing unit, but the actual thing that we want to get is a die. So on a wafer, there can be multiple dies. So finally, we might be getting a lot of dies. One die can again contain some circuit, a lot of circuits, one circuit, one device, or multiple device. It depends on our purpose. So one is intra die, that is inside the die itself. In a single die, there can be some fluctuations if there is some variability. Second is intra die. Although we are making on the same wafer, but here the device is giving some other performance. On this side, giving some other performance. This side, some other performance. This is very common. Like it is generally said that if we have a wafer, the central part of the wafer gives us the best quality in general, best quality of processors or uh, transistors, and the peripherals we might not get the best, and that's why uh, like we will discuss how it is done, that many times we already know that such variations can occur. So purposefully, some like say Intel is uh, selling a lot of i7 processors, all branded as under i7, but some of them are power processors, some of them are for common use, like if you see the number, their model numbers and all. Okay, so on the same chip with the same configuration, same architecture, on the sides what we are getting that may be taken for a low performance work, in the center one which is giving better throughput, perfectly made, that can be used for a better performance. This is generally done, but not what is actually being done in Intel. I don't know about that, but this is something that happens. Okay. Second is wafer to wafer. So we made one set of devices on a wafer, then on another wafer, we made the same set of devices using the same process, same optimization, everything. But still there is variation because either there is a systematic error or a systematic variability or a random variability. And random variability is more dangerous because for systematic variability, we can identify, compensate it, correct it. It it happens generally that once it happened with me that I was depositing some dielectric on my wafers. Every time I was getting good results, same results. Okay, but the same system is used with by different people. Okay, so in between some problem happened and some tool was repaired. Some part of the machine was repaired, and then say after a gap of 20 days, I deposited the same material, and I thought, yes, I have already optimized it multiple times and all, and I will get the same result. But I was not getting that. Then I checked that now there is a variation. There is a change that has happened. I later on I found what was the reason for it, but now the deposition, the thickness has changed. But every time, like what I was getting earlier, it was different from that. But every time the deposition now was giving same output, the same. same time I am getting the same thickness, although it is different than the one I had optimized previously. So that kind of error is a systemic, okay, where I know that okay, such change has occurred. So now I have to change the whole process. Like I have to manage the whole process based on these changes. Okay, but what if it is random, very random? That suppose that I am working today, and in say in my lab the humidity is not properly maintained. Okay, it is fluctuating. So today I might be getting some output. Next day I did the same process, some another like some other output, like A in the first day, B in the second day, and then in the in another case when say it started raining outside, humidity is again disturbed, and in this case I am getting even different output. So these are random variability, and this has to be taken in care. This can be taken care only by uh, only by taking care of the other like external parameters, like we have been discussing from the starting. Everything should be properly maintained, like the class clean room, what kind of clean room it is, the temperature, the humidity, all such things has to be maintained properly. Okay, then there can be batch to batch variations also, like we are putting 10 wafers at once, and those wafers went fine, but the next batch that again have 10 wafers can give different results. So in all these cases we have to understand what are the variability that is leading to this model. Okay, random effect, yeah. So we have already seen this, like mass flatness, resistor, like there can be different kind of deviations. Okay, so there are some tools like Monte Carlo methods that help to predict and mitigate these effects during design itself. So when we are designing, there itself, such external factors, they are mostly like mathematical models for these processes, and they take in effect, take in consideration what can be there, what are the errors, and we are putting those errors and like we are putting those variations, errors. I will not say error because they may not always lead to error. So variations. So such variations are put in simulation tools like Monte Carlo, and other tools are there that helps predict and mitigate these effects during design itself. So design rules are defined as hard rules and mild rules. Hard rules are the necessary rules that must be followed and cannot be altered. If someone is altering it, there is guaranteed, like guarantee to fail kind of rule. Okay. Then are mild rules that are recommended. That if these recommended things are done, that will lead, like we will get, uh, like these are the recommendation that will give the best output. But there can be some compensation. We can play with these rules. So when we are designing the whole process or the device, designing is for both. Uh, some people design the device, some people design the process. What will be the process followed? So they will design, they will specify the hard rules that this these things have to be followed. They must be followed properly. There will be some mild rules which are recommended in nature, but not compulsory. Okay, so but still, if these rules are not followed, they they can lead to some defects or from process. Either there can be two reasons. One is we are not following the design rules properly, or the process itself have some error, like systematic or random variation. So in this whole process, like in one case where we were talking about the mask design, there also we talked about there are critical area. Although the whole mask may be designed as one, but there will be some critical area where there will be critical thickness. The lines might be very close, and we have to understand that we must know the critical area, and we have to analyze this. So, so once the processes has been done, after each process or after a batch of processes, the critical areas have to be analyzed. Like if you are designing, say, connections, like these are big connections, but here we have small structure which is very close to each other like this. So analysis may not be important in other areas, and then here it is very thin and directly connecting. So when the process has been done, the area that will be of concern will be this. We'll check this area. We'll check whether either it is merged, like is it merged, or is it too far apart, or is it at the correct position. So such critical areas have to be analyzed to because such the areas which are most sensitive to defects or deviations. It ensuring adherence to design rules minimizes the risk of functional yield loss and improves the yield. So how do we do the process and yield analysis? Functional yield, that is, it determines if the device is functional, working or not. Just one. The device is made, now it's in working condition or not. That is how much is the functional yield. That means we planned to make 250 devices. Out of this, how many are functional, working? That means, say we got 75 devices as functional. So we will say the functional yield is 75 out of 250 devices. Second is parametric yield, whether the devices meet the required performance parameter. Say out of these 75 devices, say let's say we wanted transistors, we wanted their saturation current uh, at specific gate voltage to be, say, in the range of 100 to 120 microampere. Okay, so how many of these devices are giving the parameter that we wanted? And say we got 57 devices. So we'll say, like, the perfectly performing, although there in case of parametric yield there will be different categories, like some of devices with 5% error, some of devices like having 5% variation, 10% variation, 20% variation from the design designed parameters. Okay, so what will be the factors that will affect this functional and parametric yield? Both are important. First is functional yield, that is working or not. That is one most important. Then parametric yield. Lower the error, uh, we will get functional and parametric yield as almost same. Like if we are getting all the working device, as the best, having the best parameters that we wanted or we designed, that will give the same parametric and functional yield as same, and that is the requirement. As well as we want the functional yield to be high. It should not happen that for 250 devices we are getting 75 devices, but if we are talking about a lab scale where we are doing a lot of optimization and trial, the yield can be much less. Okay. So what are the factors? One is process variation, like lithography exposure or H uniformity. Supply voltage variation. When we have made the devices and we are testing, there also, if the supply voltage is varying, so this will also affect the device behavior. Second is environmental variation. If there is change, if we are testing it, or say we are checking the yield and there is variation, like we started in the morning, early morning, and the place where we are testing, it's not in a clean room, because testing electrical characterization might be done outside, and there in the morning it was cold, by the noon it became too hot, and in the evening it it rained and the humidity increased. So these environmental variations may lead to uh, change in temperature and operating conditions, like humidity and temperature are one of the most important variation that occurs. Okay, so that can also lead to different that will affect the yield. So these we have to take care that there is no environmental variation when we are testing and when we are actually fabricating also. Okay. Then is corner analysis, like testing different combination of process. So a combination of this, uh, if it is like we purposefully maintain different kind of environment, like say different temperature, the same device is tested at say different temperatures, different humidity, different supply variations, like we will start with 5 volt, 5.5, 6, we'll check all, then we will go down 4.5, 4, and 3.5, and we will check that for the variation we are giving, still how much it is. So that will reduce our uh, error, that will compensate for these things, supply voltage and environmental variation. That's why when we when generally we are working with sensors, we check the same sensor for a range of temperatures, a range of humidity, a range of say light conditions and these things, so that it works fine. Okay, and then we determine that what is the yield. Okay, yes, this is successful or not, so that we say that the design is robust. So this has to be done in designing process itself. To get this robust output, robust device, we have to design taking in mind all these factors. So in the simulation itself, or during the design process itself, we have to take in consideration that what are the variations, like we will put the temperature variation, we'll put the uh, humidity level, different humidity level, and do the analysis to get our design, a robust design, that and that design rules have to be followed, then we will get our perfect devices. So what are the best practices of a design for manufacturing is understanding the process limitation early in the design. From the starting itself, we must know what are the limitations and incorporate the variability analysis during the design phase. so that we may not need to rework, like, okay, this is the problem. It happens many a times that the product is made, then feedback comes, no, no, this is a problem. Then again, it is reworked, then sent, again, feedback comes. So all these feedbacks or variability have to be taken care at the beginning itself. That reduces the rework. Ensure that design adheres to the design rules for the target manufacturing process. It should not be relaxed. Okay, let it go. Oh, there, we can ignore that. Not that. We have to adhere to our design rules and use statistical simulations to account for systematic and random variabilities. So see, these variabilities we have to put in our design software simulations itself to get our output, so that it flags at the beginning itself, no, there is a problem, it might not work. Okay. Analyze the functional and parametric yield to identify and resolve issues before manufacturing. So we do the simulation, we get that no, the parameters will vary so much that we cannot go for this fabrication. Then we tweak it, we change it, and then we get that now it is perfect, like acceptable. Say the throughput is, say, 90% now. We can go for it. So actually we might get something around 70 to 80% output. Considerable. But what if during the design itself, what we made, if we check its parametric yield and it will give, say, only 40% will be successful. Then during the process and all, it might give us 20% yield. And that is not a good yield. Okay. So we have to take care of manufacturability while designing the device and the device processes. So by implementing the DMF principle, design are more likely to be successfully fabricated with higher yield and lower cost. Okay. Any questions still here? Yes, anyone?
No questions. Thank you.
No question. Okay. So yeah, okay. So what are the defect? Like how do we, like we saw that this is what we have to implement, but how we do the analysis and how we understand the quality metrics. So one is, what are the defect, okay, and why they are so relevant? Because defect are simply some anomalies or some problems, that something that is undesirable is simply a defect, we can, and they can grow over time. So if, say, we ignored it, okay, fine, that's very small. But over a period of time, say there was a trap or a simple metal ion was left on the wafer, okay, and over a period of time, it started accumulating other things. It started a chain of reactions. So over a period of time, it will grow and affect the device's reliability. So some marginally passing devices, like we say that we defined a border of, like, okay, yeah. So let's, this graph, you are able to see what I'm drawing.
Yes.
Okay. So suppose that we have a simple transistor, and transistor you can consider as switches. Okay, they are voltage controlled switches or current controlled switches. So if we are talking about MOSFET, they are voltage controlled switch. That means for a specific value, they will be on, specific gate value voltage, they will be on, For other gate volt like below it or say above it, they will be off. Okay, so below is the voltage and current. I am talking about gate voltage. Okay, so for this part, ideally, say this till this voltage V by 2, say it should be off, and just after V by 2, it should be on. This is what an ideal transistor characteristic should be. But when we are making, it will be something like, say, it will actually be something like this, or say, no, it will go till here. Okay. So what we will consider, that whatever current above this is a on, and below this is off. But if we have a device which, while fabricating, we found a device which is something which has a characteristic like this, and then like this, very near the threshold where we are defining the on and off. The chances, so this has marginally passed, though it is fine till this voltage, it is off according to our rule, and after this voltage it is on according to our rule, but it is very marginally on and very marginally off while testing, and that can lead to, in future, that will lead to uh, some problems in future, and that will cause the customer dissatisfaction. So we checked, okay, it is on and off, but what is the quality of this on and off? That is a question. And if it passed during testing, and if we say, okay, let's put this in a, say, our mobile phone, okay, so over a period of time, it will start behaving randomly. Some small changes can easily happen, okay, and then it will not work, okay. Then to compensate this problem, we might need some additional cost, testing, additional cost, and these things. So the solution for this is tighten the quality matrix window to only pass devices with strict parameters. So we can define that the on will be this portion, off will be this portion, just this much. Small window, making it strict. We cannot make it very perfect. No, this only. That's not possible. Okay. So we have to make the quality matrix window very strict. So this will improve reliability, but will increase unit cost. Because we are making it very strict, it will increase the unit cost. Then we have to take in consideration the cost also, because we cannot sell every device at a very high cost. Okay, so because we have went like, best solution is have very strict uh, matrix, strict parameters. So this, but having strict quality control reduces the yield, because now in a wafer, out of 250 wafers die, say only 4 or 5 die is successful, fitting into our strict quality control. In that case, we might not, uh, like, we will actually reduce our yield. Okay, so we have to, like when we are manufacturing or if we are taking seeing it from the point of view of a manufacturer, we have to do the cost and quality equation. We have to understand the cost and quality equation and ensure such that it should not be very strict, but it should not fail also. It should not be so relaxed that it fails. And it is very cheap. Say we are getting uh, i7 processors in, say, below 1000, but it works fine only for 15 days. No one will take it. But if the same processor we are getting for, say, 7 8 lakhs, but it works lifetime, still only few will be able to afford. So we have to compensate, or we have to understand that, okay, say we take a processor that costs, say, 10 20,000, and that can work fine for, say, next 4 years 5 years, no problem. Okay, that we have to understand. So uh, how this is done? This is done by using a feedback loop. That is, first batches provide crucial feedback to designers to improve the next batch of devices. So one batch is made, from it testing is done, feedback is taken, and designers take in those inputs and improve the device. One is, we what problems we know from manufacturing, we already incorporate. Second way is, as the batches are made, as the devices are made, we again take feedback and improve our design. We improve our process. Then there is another relationship between die size and yield.
One question,
Yes,
Vikas,
yes,
please.
yeah,
In the previous slide,
yeah,
okay.
mhm,
Uh, Now, in the graph, what you're explaining,
yeah,
orange line was
yeah,
our first device, right?
yeah. One device,
Huh?
yeah.
Huh.
Huh.
Orange line had a wider tolerance limit,
Tall.
right?
No, no,
Our
like that was fitting more into, like, that was not a perfect device, but it was somewhat a realistic
close,
device, close to,
huh?
yeah,
Perfect device, right?
yeah,
Then the blue line was a not a good device.
not a good device. Yes,
Huh. We reduced the inference space. So between orange and orange is better.
yes,
Huh? How we are, how reducing the tolerance limit can eliminate the blue device, but
yeah,
while still keep the orange device.
yeah. So, like, I think I should use a different color here. Yeah. So first, first tolerance limit was this, right?
Hmm.
Now we are putting two tolerance limits. For on, we are putting this tolerance limit.
Hmm.
For off, we are putting this tolerance limit.
Hmm.
Now you see the blue will not fit in these limits. This is
Hmm.
the lower limit of on, and this is the upper limit of off. So now the blue one is not fitting in actually both of this. So then we will ensure that, yes, that is, so, like, if someone from a bit of VLSI background will understand that that is what is generally done. And this is called as noise margin, and these things, there, like a separate chapter is there in these things. So this tolerance, and as we will make, someone might say, then why to go for this one? Let's make the tolerance limit, say, uh, a black one. I will say this only, just this thickness, and this one. So for this, we will reduce the yield a lot, because we might be getting only, say, out of 400, 500 devices, we might be getting only 4 5 perfect devices. So if we are discarding all others, we are at a loss.
Correct, correct.
Yeah. So we have to take in consideration both the things, that one, we have to get good devices, but it should not be like, it's fine if it is very good, but it should not be so good that we are not able to produce it.
Right, right.
Okay, so we
So
have to
why I got confused na ki
yeah.
tighten the quality metrics, but we are actually increasing, means in
Okay,
size
you
we
are,
are
yeah, central
increasing.
part you
So
are, no, that is the top part. That is lower limit of on, and
hmm,
below is the upper limit of off.
limit of one. So separate. ठीक है, correct, correct.
Separated, yeah. The
Hmm.
same thing is separated now.
Okay, thank you.
Yeah. So there is a relationship between die size and yield. Okay. Re- The defect density remains constant regardless of die size. Okay. The defects will remain, whether it is this small die, this big die. Fine. Smaller die size leads to a higher number of usable dies per wafer. So if we have a wafer and we are slicing it into smaller dies, the devices are actually small. Like the die size is small. That will lead to higher number of usable die. Okay. So our yield or throughput will be large. And if we have larger die, okay, larger die means in a wafer also the quantity of dies will be less because there will be big devices. Okay, so the greater impact of defects will be there on the yield, but that is it is not always feasible to reduce die size. So uh, due to application requirement or technology limitation, say like it is not always possible to make things in nanometer range value. If we do, we in this course we are only talking about this nanofabrication, but when we shift to nanofabrication, there are a lot of things that come in play. There will a lot of things that were not relevant when we were talking about big devices that becomes relevant. Small like when we talk about flowing electricity in our homes, we are never concerned that two wires are close to one another. They will affect each other. That's not a concern since that effect is very less when we are like flying like when we are doing the wiring in our homes. You might see that a bunch of wires go and all of them carrying current, not an issue. But what if the distance between these two wires is in terms of nanometers or micrometers? They will have a tremendous effect on each other, and that also the current is itself in nanoampere or say microampere. Okay, that effect increases. So reducing the size of die or reducing the size of device is not always feasible. Although reducing it will increase our throughput. So that's why a lot of work is being done in this field to reduce, and further reduce it. Okay. So we can overall take that integration of design and manufacturing, like we have to consider the manufacturing limitations to ensure they are practical and realizable. Okay. Ideally, someone can say, so let's make it so small that directly electrons can flow. No need to have wire, no need to have such thick wires. Let's electron flow. We will make a tunnel and let the electron flow in SiO2. But that's not feasible. Okay. So we have to ensure that they are practical and realizable. The tech, they might be possible, say, down the line in next 10 years, 20 years, 100 years. But at present, what are the practical considerations we have to take? Second and most important thing is design feedback loop. You have not, you don't have to get offended when someone says that these were the problems in the design. These problems happen. Okay, we have to take the feedback from the process. We have to take what are the problems and we have to correct it. We have to improve it. We have to put it in our design that these problems has been removed. So, and one important thing is that we have to balance between optimal design and manufacturability. It should not be such a strict parameter that we are not able to manufacture it perfectly, and it should not be so relaxed that we are not able to get the perfect output. So we have to do a analysis between good yield, reliability, and cost efficiency. It should be cost efficient. Technology aware design. So next is whatever technology you have, okay, focus on designing for that technology, not just the application. Like we have a technology of say to make something of 180 nanometer, and we are designing it for 50 nanometer because that is the industry standard. But in your facility, it is 180 nanometer. So you will have to design according to the things that are available to you. Okay, you might be knowing things of 50 nanometer and these things, but you have to take in then like consideration what are your limitations. It so it is better to have a suboptimal design with a high yield than a perfect design with low yield. So this is something that we have to keep in mind, that it it is fine that we have a design that gives good yield and good work instead of a very perfect design that gives the perfect output but yield is low. We don't get devices frequently. Say in 1 year we are able to produce five computers and they work very well. Will you be able to maintain your company or whatever you are running? That's not possible. So these are so no, these are limits. Okay, so simply it is like design, then fabricate, then check the yield, and then check the reliability. Okay, these are simply the same thing. Okay, so there are different simulators like lithography simulators that allow designers to understand edge effect, corner rounding, and proximity issues. So we have learned about lithography a lot, and we talked about that lithography is a major process in the whole system. Okay, the whole micro and nanofabrication. Lithography is one that uses a lot of resources and lot of time and money is put into it. Okay, so there we talked about edge effect, corner rounding, and proximity issues. All these are built into our lithography simulators. Okay, so based on that, and it will even sometimes there are some tools which will give this feedback to what are the corrections that we can do and what are the layout considerations. So while designing the mask itself, some corrections it will suggest, so we can do those corrections, or we can go for physical model simulation. That is what will be the timing and like parametric issues in high speed and complex. So once these are done, okay, we will check what will be the issues. So the design itself, what can be the issue? Once the design is made, what will be the effect of it in the circuit and all? It might be that the device is made perfectly, it looks perfect, but it will not work in real life. Like it will not carry current according to our need. So these things have to be done. So that will improve the yield by addressing the optical and process variation in the design phase itself. So how do we do the lithography friendly design? This is done using design rule check, DRC. So whenever we are say when we send our mask to the printer, like who makes the mask, okay, they do the DRC. Okay, they ensure the design rules are followed to avoid process variation. Okay, so there are two approaches to design. One is wide range design that allows more design flexibility but can have suboptimal yield due to varying process windows. Okay. Second is restricted design. That is, it will say that no, the design window is very less. You can have a thickness of any thickness that you put will be between 10 to 20 micron. Not like flexibility is less. Okay. Or say everything, nothing can go below 10 micron, nothing can go above 50 micron. All the features should be like that. So you will get a very uniform mask, all the patterns of almost similar sizes and less variation. In this case, we will get better uh, controlled structure, high yield and reliability, but designing will be much difficult. All the designs you have to like design using this restricted design. In case of wide range design, you say that these are critical things that you cannot go below, say 10 nanometer is our lowest limit. Highest limit is, say, we are saying 500 microns. That is a very wide range. You can design a lot of variations, but that will give suboptimal yield because in some regions it will give good output, in some other region it might not give. Okay, so we have to we have to follow the design rules. So whenever we are doing the design, we have to understand what are our design rules, and if either we are going for wide range design or restricted design. Then we have to go for proximity correction. That is, there we have to design such that it ensures the physical limitation. It might be that with uh, with the technology available to us, we know that theoretically this is possible, but physically, what are the limitations? Based on that, this proximity correction has to be done. Okay, how do we make the lithography aware circuits? It is first we design the initial layout, then do the DRC check, that is we are following the design rule compliance or not. Adjust for lithography effects, that is diffraction, interference, and these things, that it is too close, it might get diffracted. It is it is having some crossover and these things. Okay, then we do the parametric extraction, timing, what is the synchronization that will be done if it is in EBL and all. Okay, so this will define the printability of the design. Then we do the mask preparation, and then we do the inspection, like we will check all the critical areas and all. That will ensure that we identify and correct hotspots, any critical area, and ensure that the design meets performance and yield requirement even before we start the production. Because here we are talking about design. So mask is a design, okay, of the process that we will do later on. But the mask itself, if it has problems, it will lead to a lot of problems. So we have to ensure that at the starting itself, that is the designing thing itself, we are having a good, like a perfect design, as perfect as possible. design so that we are able to get better, like reliable, optimal, and good yield. Okay. Okay. These examples. Yeah. Okay. I will put this. These are just, yeah, one part is important, I think. Yeah. These cost and all. One way of is one way to ensure good throughput is using multi-prototype testing. We are talking about one wafer with same kind of design throughout. But this technique is that will actually ease, or you can say reduce the testing time. Okay, like on a single wafer, we are dividing this as quadrants, ABCD. Okay, same process, since this is on the wafer, same process will be followed for all the devices, but they will have different design. Part A will have different design, B will have different design, C different, D different kind of dice, different parameters. Okay, say I know that these are the variations, so I will. Uh, what are the possibilities that can work? So say B is the perfect one that should have worked if there was no variation. In C, I have done some positive variation, A some negative variations, D some more positive variations, say, okay, in the dimensions or all. Once this whole process has been completed, everything done, then we will check what gave which of these gave the best output, best throughput. Okay, suppose that uh, C is the one that gave the best throughput. So from the next design onwards, we can directly put the design that was on C on the whole wafer, and we can go for a better one. Like we will get better throughput, better yield. Okay, so these kind of testing we can do for testing where we have shared processor. The process will be same, like say deposition, lithography, etching, and then again passivation, and then electrical testing. In all these cases, but say for different dimensions. For example, let's say I want to test that for a good sensor, what should be the difference between, say, these ID pattern kind of things are used in sensors where they have finger kind of structure. So what should be the optimal distance between these? So say for the A, I kept 100 micron, B, I kept 120 micron, C, I kept 140, D, I kept 160. Like that, I divided the whole wafer, say not exactly in quadrants, say I divided into different zones. Okay, say 10 zones, and I did different kind of, and the whole process is same, just the dimensions are varying. And once done, I tested which one gave the best output. Okay, say I got that at 160 micron, I am getting the best output. Okay, so I'll stick to 160 from the next time onwards. Okay, so this is multi prototype testing. This is a good way to reduce the cost of testing. In the same wafer, we are putting different quadrants. Since in wafer, if we are dealing with wafer, the variation is generally from center towards the like towards the periphery, and that's why uh, the testing is generally done by dividing the wafer in quadrants, because central part, like all of them should get equal opportunity, like equal kind of exposure. So in the central part, all the four quadrants or six quadrants, if you are dividing, they will get equal kind of treatment. Okay. Hello. Uh, are you able to hear me now?
Yes. Yes.
Yeah. Okay. So till here, any questions? Okay.
No. No. No questions.
Okay. Yeah. These are, yeah, this I will just put. This actually in the last lecture, sir has discussed one example, like a case study kind of. So this is something we have related to that, the summarization of it. Though, so this is just the repetition. Like in CMP, one thing is done that is important. That is, dummy fields are used to improve CMP. Like suppose that uh, this is a structure, okay, which we have to planarize. Okay, so there is a gap in the in between these structures. So to planarize it, yes, you are saying something.
No. 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 No.
Yeah. So to planarize, if we just keep these areas open, they might get damaged during the process of planarization. So sometimes a dummy filling is done. Say it is filled with such a material that we can easily remove afterwards. Say just dip in water and it will remove, or say dip in acetone and it will remove. And then we do the uh, like planarization. Then we will get better output. It will, so that this abrasive material don't get inside the structures. Okay, these things have to be done. Okay, multiple contacts are given, like for the same point, same connection, not just one connection, two, three connections are given. So if one fails, we will get a redundancy is given. Same structure, same connection, but two, 3 points. So even if this point is not given, like this is a structure that we have to connect to something. So we made a pad like this and this. So if this first wire fails, first connection fails, the second will work. Or say we make five, out of five, at least two will work. So our throughput increased. That's why uh, sometimes you might see that in case of transistor packaging, uh, like now uh, a header is used, which will have six legs, six legs coming out. Ideally, we have three terminal only: source, drain, and gate. But all of these terminals are connected to two pins. So at least one of them will work. Okay, such things are used in this to ensure reliability. That saves cost because the rejection ratio, the breakage, and these things will reduce. Okay, and we have to ensure there is less misalignment. If there is misalignment, we must understand properly that what is the systematic error, and we have to compensate for that. And then uh, the designer should have process knowledge. It is very common in case of these designs that what circuit you expect is made by someone who is totally unaware of what are the fabrication processes. And that's one big reason that people should like people working in this area designing this should know about the micro and nano fabrication. They should be well aware of the limitations. They should have the process knowledge. Okay, and simply they should collaborate with the process engineers. In a sense, the design engineers and process engineer should collaborate to have a better output. Okay, so there are some questions like in chemical mechanical polishing, the wafer is loaded on the polishing pad, conditioner head, polishing head, or none of the above.
Polishing pad.
So,
Polishing pad.
yes, any why polishing pad?
like uh, that.
It's the polishing head. It's just the name. Okay.
Oh,
The wafer is mounted on the point that is polishing head. Okay.
okay,
And
okay.
then on it, the polishing pad is the one which has the simply
Oh,
like the sponge like thing that not exactly a sponge that just rotates the abrasive materials. Okay.
ठीक है,
Head
ठीक.
on head, it the pressure is applied. Okay. In CMP, select the right answer. Spatial variation in angular velocity results in variation in material removal rate across the wafer. Material removal rate depends only on abrasive material particle size in the slurry, or non-uniformity in device density across the wafer can result in uniform global planarization.
Okay. A, the spatial variation
A,
in
yeah,
angular velocity,
yeah. In B, why B is wrong?
because it is only dependent. It depends on pressure.
Yeah, it depends on pressure, relative velocity, these
Velocity.
things also.
Uh,
And non-uniformity in device density
can
will
relate
actually, yeah, will not,
non-uniform.
yeah, non-uniform global planarization.
Hmm.
Okay. In the topography in the silicon, if the topography in the,
And
you are able to see this image.
yes, yes.
So
This is guys and
this is 100 nanometer, this topography, and the topography of silicon dioxide on silicon after polishing is 20 nanometer. So this difference is 20 nanometer. With a planarization distance of 500 nanometer, what is the planarization angle in degrees after polishing? Choose the closest angle. So what will
okay,
be the best angle here
okay.
for
Then
good planarization?
hmm, then that 80 divided by 500, and that theta we have to calculate, right?
Yeah.
Uh, but so tan inverse of 80 upon 500. I don't know whether it is tan inverse or which inverse.
Mhm.
But okay, wait, shall I do the calculation? Just
It is, you can say, simply the lowest value that we get.
okay, okay,
Okay. It is the lowest value we can get, 11 degrees. Like this is the lowest. Okay. We can go further.
okay, okay. 9 degrees it is giving, but
Yeah, yeah, lowest
hmm,
near to that.
okay,
Yeah,
11 degrees.
yeah.
Okay,
So the lowest planarization angle, best output. Okay. Closest calculate here is 180, 18, sorry, 11 degrees.
okay. Your voice is echoing like
Just a minute, let me check. I think. Hello, now is it clear?
yes.
Okay. So in CMP, dummy fillings are added in the design along with large trenches or opening to avoid erosion, desync, or planarization.
Dummy fillings are
Like,
added.
yeah,
Ah,
dummy,
yes, yes. You
uh,
taught just now.
yeah, dummy filling. So if we are putting dummy fillings, will it
Cause
reduce
erosion or
erosion,
dishing.
desync, or planarization?
So, uh, concave surface, if it is happening, then dishing will happen. Erosion and density. It is not erosion.
Yeah, it is desync.
Dishing.
Okay,
Okay.
which is because erosion is mostly due to difference in material
Hmm. Density variation. Yes.
density variation that will still happen
Yes.
even if dummy filling is there. Okay.
Right.
So wafer to wafer variability is caused by spatial variation, temporal variation, both, or none of the above.
Temporal means with respect.
To time.
Spatial means with
To space means in the
effect.
wafer
Yeah,
itself,
yeah,
right?
yeah.
So wafer to wafer, it is not. So it is both then.
Both. Yes.
Both.
So wafer to wafer variability due to
Hmm.
spatial as well as temporal.
Time. Hmm.
Yeah. So parametric yield depends on contact failure, metal interconnect failure, metal interconnect thickness variation, or all of the above.
Parametric field will depend on all of the above.
Yeah, because it is how well it is performing, not just
Correct.
on or off.
Correct.
Okay. Okay. Now, a process engineer has processed a wafer that contains 9 dies, like shown here. Okay.
Hmm.
After characterization, the device in corner die 1, 3,
Three,
7, and
seven,
9
nine.
were found to be faulty. Select the option that could have caused the issue: lithography, resist process, etch process, or all of this.
Uh, Possibly lithography, the corner, all our corner
All are corner.
devices.
Yes.
That is why possibly lithography.
Yeah. In fact, if lit one
Okay.
process is faulty, all other processes will also be faulty. That is the thing, that if resist was coated improperly, it might happen that at those points the resist was thick. Okay. Then lithography will be wrong by default. Then etching will also be wrong. Okay. So these are very much dependent processes. That is why this actually last 2 weeks are covering these things, because we have to understand that these processes are not independent of each other. They are dependent on each other.
Okay.
For
Okay.
for a given defect distribution and density within a wafer, which of the following statement is true? Increasing the die size will decrease the yield. Decreasing the die size will decrease the yield. There will be no change in yield.
Decreasing die size will decrease yield.
Decrease yield. No, increasing die size will decrease yield.
No, no. For given defect distribution and density within wafer, right? So
Hmm.
defect, d- uh,
Yield
num, acha, number of defect distribution and density. Number of defects are same or not same?
given
Defect
fixed,
distribution and
fixed,
density.
fixed. It is
So
fixed.
number of defects are fixed, right?
Fixed, yeah.
If number of defects are fixed,
Number of
then
defect
oh,
distribution and density is fixed.
so number is not fixed, then increasing die size will decrease it.
Decrease the yield, because we will have more defects on the same, like
Hmm.
one single die.
Correct, 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 correct.
Design for manufacturability is also called manufacturing for yield, technology aware design, or technology limited design.
Like
This is
manufacture
just
for it.
it is also called as technology aware design, where you know the technology beforehand.
Okay.
Okay. Particulate contamination will lead to which of yield loss, systematic or random?
Random. Random yield loss. Because why I'm saying random is because where the particulate falls on the uh, die, that we are not controlling, right? That is why it can yield to random yield loss.
Yes. So it is random.
Hmm.
Okay. So any other questions? We will continue with process integration in the next week. And on 10th in the evening, it is just an extra session, 10th
Okay.
6 p.m.
6 p.m. Huh?
Yeah, 10th 10 10. Yeah.
Oh,
So that is just I will that is from my experience. Like, the course is from some like the professor who are much more experienced in this field. But yeah, what I know, what are my experiences, and what is the overview of the whole process, that I will be covering in that session. And we can have good interaction, even some topics if you want to discuss that, yeah, these topics we can discuss, we can discuss those topics and these things in that class. And then we will have the last class of this whole series on the next Tuesday.
Tuesday.
Yeah.
Okay. No, no, thank you. Like these are really very helpful, and you teach also nicely. So
Thank you.
that is very. Just time. Can we move it to 7 p.m.?
Actually, that's already, I have already given the time to, like,
Okay.
to
Fine, fine.
discuss
I
the
will
topic.
adjust my time. No problem. 6 p.m. ठीक है. No problem.
Thank you all.
No, no worries.